Hi folks, and welcome back to Math with Captain Rod. I'm making this video here to finish up the application part of the geometric series sequences in your homework. So we're going to take a look at this one, which is number 18 here in your handout. It says a ball is dropped from 10 feet. It rebounds to 60% of its previous height. How high does it make it on the fifth bounce? So that's pretty much what it says. I shortened it up a little bit. So the idea here, physics people, we love our pictures, is a ball starts here, starting at 10 feet, and then it does this, boing, and makes it up to 60% of its previous height. Boing, 60%, boing, 60%, boing, 60%, and so forth. So if I were to write some values representing the height, the first one is 10. The next one is going to be 60% of that. The next one is going to be 60% of that. The next one, I'm going to use a calculator here to do that one, is going to be 60% of that, and so forth. Now again, the easiest way to solve this is to probably just run this out to 5 bounces, right? So this is 1 bounce, and 2 bounce, 3 bounce, 4 bounce, 5 bounce. We would just have to hit it with a 0.6 2 more times. But I'm going to go ahead and write out a formula here for the nth term, recognizing this is a geometric sequence because it's a 0.6 that gets us multiplication of 0.6 that gets us from here to here and then here to here and so forth. So this is going to equal 10 times 0.6 to the n minus 1. And again, this first term is for n equals 1, and this one's for n equals 2, and so forth. All right, now make it on the fifth bounce. So this would be for the first bounce. This is how high it makes it after the first bounce. You'll notice that the n is 2. This would be the second bounce, and you'll notice n is 3. You'll notice that basically my value for n needs to be 1 higher than the bounce number, so to speak. So for the fifth bounce, we're going to want to use n equals 6. And if we put a 6 here, minus 1, that's going to end up to the fifth. I'm going to go ahead and calculate a value. Alright, and I get 0.778 feet. Honestly, 0.78 is fine. Even 0.8 is just fine for this problem. So I'm going to call that done. I think I'll pause it here while I set up for the next one. Alright, I'm back. And the next one is about a water spa. Let's see. I shortened it up quite a bit, but basically we have a spa that's starting at 70 degrees, and it's increasing at 5% per hour, not 5 degrees per hour, 5% per hour. Find the temperature after 4 hours. So let's see, if we're increasing 5% per hour, let's talk about that first term. The next temperature is going to be 70 plus 0.05 times 70. Which is 73.5. Now, notice here that if I wanted to, I could take the 70 out, and then I've got this 1 plus 0.05. And notice that that's equal to 70 times 1.05. So increasing by 5%, you can either, calculate 5% of 70 and add it, or we can do 1.05 times 70. Now, after another hour, we can take this and just multiply by 1.05 again. And after another hour, times 1.05 again, and so forth. So basically now, let's see, I'm going to write this out. So we got 70 is the first one. Next one is 73.5 out to some a sub n, where the a sub n can be described by a geometric sequence equal to 70 times 1.05 to the n minus 1. And again, this first one here would be for n equals 1. And what we're looking for here says find the temperature after 4 hours. So here's our temperature after 1 hour, the next one would be after 2 hours, and so forth. Now notice that after 1 hour here, we would use a value of n equals 2. After 2 hours, we'd be using n equals 3. So after 4 hours, we're going to use n equals 5 here. So what we're calculating is A5, which is going to be 70 times 1.05 to the fourth. And let me give me a moment here. I'll give you a value. And I get a temperature of 85.1 degrees. I think 85 degrees Fahrenheit is good enough for that one. I'm going to go ahead and call that done and set up for the next problem. All right, I'm back, and we're looking at number 20 here on the application section under geometric sequences. So it says, basically it says, a piece of land that is originally valued at $20,000 is increasing in value 12% per year. What is the value after 10 years? So let's see. The first value here is 20,000. I'm going to go ahead and write that out. Then the next value is going to be this. This number times 1.12. Which is 22,400. The next value we'll get by taking this and multiplying by 1.12 again, and then the next value by taking the previous one and multiplying by 1.12, and so forth. So what we're looking at is a geometric sequence out to some a sub n here. The a sub n can be described by taking our first value, 20,000, and multiplying by our r. Now to get from here to here, that was a multiplication of 1.12. And then from here to here, multiplication of 1.12, and so forth, to the n minus 1. And again, this is true for n equals 1. And let's see, what we're looking for is the value after 10 years. You've got to be cautious with this and make sure you put the right value in for n. So this would be after no years, basically. This would be after 1 year, and notice that n would be 2. And then after another year, n would be 3, and so forth. So you notice that the n value is larger than the year's value, I guess, by 1. So what we're going to want to calculate here is A11. 1.12. And when we take 11 minus 1, we get 10 as our power. So let's see what we end up with. 1.12 to the 10th power times 20,000. All right. And I get 62,117. And what we have here is apparently a very happy landowner. I'll just take a moment here and make sure that looks right. 10 years, 12% is pretty high. Yeah, I think that's probably pretty reasonable. All right, so there's the value of the land after 10 of these cycles. Just going to calculate that one more time. Yep, got the same value second time around. So this should get you finished up on your notes under the application for geometric sequences. If you have any trouble with the homework, send me an email. Have a great day.